Hello friends, welcome to the video lecture series on digital image processing. I am Dr. Alpesh Dafda, and in this 40th video class of DIP, we will study arithmetic coding in digital image processing and its implementation in MATLAB. Arithmetic coding is a form of entropy encoding used in lossless data compression. Now, what is the meaning of entropy encoding? Entropy encoding means it enables to represent an image in a more efficient way with smallest memory for storage and transmission. See, although the Huffman coding, which we learned in the previous video class, is the most popular technique for lossless data compression, it is not always 100% efficient, right? Hence, we search for other lossless compression techniques like arithmetic coding. So let us start. Arithmetic coding is also known as range coding. Why? Because we are assigning a code within a range of 0 and 1. Okay, it is also a type of lossless compression algorithm, and we get the same image at the output, so there is no data loss. And we know lossless algorithms are always used where reliability or data preservation is the main factor, for example medical imaging, right? For arithmetic coding, the sequence of source symbols are encoded together, which is not the case with Huffman coding, and there is no one-to-one correspondence between source symbols and code words as there is for Huffman coding, right? Arithmetic coding takes in a complete data stream and output one specific code word, which is a floating point number between 0 and 1 with as few digits as possible, okay, so that the entropy is achieved. As the number of symbols in the message increases, the interval used to represent it becomes smaller, which means longer the bit stream, more is the precision of the output number. So when the number of symbols in the message will increase, the decimal digits after 0 point will go on increasing and it will become a more precise output number. See, arithmetic coding is also a variable length encoding like Huffman coding, right? But Huffman coding encodes source symbols one at a time, which might not be efficient, while arithmetic coding encodes sequences of source symbols to variable length code words. Arithmetic coding is a non-block code, which means that arithmetic code does not generate individual codes for each character like Huffman coding, right? And the efficiency of 100% can always be achieved using arithmetic coding, which is not always the case with the Huffman coding, right? We know that this efficiency is equal to entropy upon L average. So this efficiency of 100% can always be achieved using arithmetic coding, as entropy H will be equal to L average, and hence it also satisfies Shannon's first theorem of noiseless coding, right, which says that minimum coding bits should be equal to the entropy H, which is obtained by arithmetic coding. But this happens only theoretically, right? And practically it is not possible. Why? Because the difficulty for arithmetic coding is practical implementation of long messages is not possible, as arbitrary precision floating point library or registers are not there. Theoretically it can achieve 100% efficiency, and also it works good for short messages or not very long messages, but when the messages are very long, the 100% efficiency cannot be achieved practically. Before understanding arithmetic coding mathematically, let us understand the differences between Huffman coding and arithmetic coding. Huffman coding is more popular as compared to the arithmetic coding. Huffman coding is not always optimal. It will not give you shortest code word, right? But arithmetic coding is always optimal. Huffman coding is simpler technique as compared to the arithmetic coding. The compression ratio of Huffman coding is poor, you can say, but the compression ratio of arithmetic coding is very good. Conversely, the compression speed or computation is very fast for Huffman coding, whereas the compression speed for arithmetic coding is slow. The memory space that will be required for Huffman coding will be more and compression will be less, right? Whereas the memory space that is required by arithmetic coding is less. For Huffman code, precision is not an important factor, while precision is a very important factor for arithmetic coding because of different floating point digits after 0 point. Okay, these are the steps of arithmetic coding. Arrange the characters of string or numbers into ascending order. So it may be strings, as we will just see in the example, right? Or it may be numbers or pixel values of a digital image. So we have to arrange them into ascending order. We have to divide the numeric range 0 to 1 into the number of different symbols present in the message. Now we will expand the first letter to be coded along with the range, and further we will subdivide this range into number of symbols, and this procedure is repeated until the termination character is encoded. So what will happen? A sequence of source symbols is assigned a single arithmetic code word which corresponds to a sub interval in 0 to 1. So smaller intervals require more information units, that is bits, to be represented. Okay, let us first understand the example given in the textbook. Say this is the message we want to encode. So we will arrange these symbols in the ascending order like this, and these are the probabilities. Now we will assume that the message occupies 0 to 1. So this is 0 to 1, and we have to subdivide this 0 to 1 based on the probabilities of A1 to A4, and then we will go on updating the interval by processing source symbols. So A1 probability is 0.2, so initial subinterval will be 0 to 0.2. A2 is also 0.2, so 0.2 plus 0.2 CDF will be equal to 0.4, so 0 to 0.4. Similarly, 0.4 to 0.8 and 0.8 to 1. So now this is the encoding sequence. 0 to 1 is now divided into 4 divisions having probabilities 0.2. This is again 0.2, 0.4 and 0.2, but the CDFs will be equal to 0.2, 0.4, 0.8 and 1. So encoding A1 first. So we will enlarge this A1 portion, which is equal to 0 to 0.2. So total value is 0.2 now, and now we will subdivide this 0.2 again into 4 divisions, right? So this value is 80% of 0.2, this is 40% of 0.2, and this is 20% of 0.2. So the values that we will get, we will write over here. Next is A2. So now we will enlarge A2 portion, and similarly we will next encode A3, again A3 as it is occurring twice, and finally A4, and we see that finally we will be getting the values from 0.0624 to 0.0688, and any value from these values can be chosen as the code word, which is also known as the tag. So here the tag is a unique identifier, which is a binary fraction, is used to represent the 5 symbol message. So normally the tag is the lower value of the last encoding or average of lower and upper encoding. Okay. Now how to decode it? Okay, so for decoding also we know the symbols and the probabilities, right? So the symbols and the probabilities are written like this, and say you want to decode 0.572. So first we have to see where this 0.572 is occurring in this 0 to 1. It is occurring in between 0.4 to 0.8. So this will be enlarged. So this is A3. We will write A3 over here. Again, this will be subdivided as per the probabilities, and we will see where this 0.572 comes. So now again it is coming in between this value and this value. So next symbol is also A3. Third one will be A1. Similarly, next one will be A2, and final one will be A4. So for 0.572, the decoded string is A3, A3, A1, A2, A4. Let us understand this arithmetic coding by taking one other example of a string of characters, which we will also implement in MATLAB. Now say we want to encode the message Dafda, a character string, right? So first step is we have to arrange the symbols in the ascending order. For these characters, A is the first character that will come in ascending. So we'll write A, then D will come, and then F will come. And D and A are repeating 2 times. So the PDF of A will be equal to 2 by 5, which is equal to 0.4. Similarly, PDF for D is equal to 2 by 5, which is equal to 0.4 again. And F is occurring 1 time, so its PDF or probability will be equal to 1 by 5, which is equal to 0.2. We know how to find out the CDF. Next, we will subdivide these probabilities in between the interval 0 to 1. So probability of A is equal to 0.4, D is equal to 0.4, and F is equal to 0.2. So the CDF will be equal to 0.4 plus 0.4, 0.8 plus 0.2, 1. Okay. Remember one important point, that the characters which we have arranged in the ascending order, we will start from below, that is nearer to 0, right? So first will be A, second one will be D, and last one will be F. Okay. So remember this, otherwise you may get false results. So first character is D. Okay. So we will enlarge this D. D is from 0.4 to 0.8. So we will enlarge or expand this interval. Similarly, we will expand A, F, D and A ahead. Now the difference value in between 0.8 to 0.4 is equal to 0.4. So you can take 40% of 0.4 and find the next value, 80% of 0.4 and find this value. Okay. Or else you can use the formula upper limit is equal to lower limit plus difference into probability. So you want to find out this upper limit. So for finding out this upper limit, the lower limit for this is 0.4. So we will write here 0.4 plus the difference in between 0.8 to 0.4 is equal to 0.4, right? So difference is 0.4 and probability of the first division is 0.4. So we will write 0.4. So this comes out to be 0.56. So the upper limit that we have found out is 0.56. So this upper limit is 0.56. Again, now we want to find out the upper limit this one. So again the same formula, upper limit is equal to lower limit now will be 0.56. Okay, so lower limit is 0.56 plus difference will remain the same 0.4, 0.4 into probability for this particular division for D is again 0.4. So we will write again 0.4. This will come out to be 0.72. So this upper limit is now 0.72. Again for the last character f, upper limit is equal to lower limit, that is now 0.72. 0.72 plus difference will remain the same 0.4, 0.4 into the probability of f. Okay, and the probability of f is 0.2. So remember, you have to take the probability and not the CDFs, right? So this will come out to be 0.80. And here you can see the upper limit is 0.80. So in this way, you can cross check whether you are going correct or not. Okay, if you are not getting 0.8, that means there is something wrong in your calculations. Okay, so this we have encoded for D. Next character is A. So A is this one. Okay, so what we will expand? We will expand this portion, A portion, from 0.4 to 0.56. Getting it, right? So again, we want to find out this upper limit. So upper limit is equal to lower limit plus difference into probability. So lower limit over here is 0.4 plus now the difference between 0.56 and 0.4 is 0.16 and the probability for first portion is 0.4. So this will come out to be 0.464. Now we want to find out this upper limit. So again, upper limit. Again, we will find out this upper limit so that we can cross verify our result. So this comes out to be 0.56. So if you are getting 0.56, that means your calculations are correct. Now next character is F. So now we will expand the F portion, right? But now as this is the last character, we can choose any value in between the upper limit and the lower limit. Normally, the lower limit is chosen as the tag. For the last character, the lower limit is 0.5408 and the upper limit is 0.54592. So the tag or unique identifier can be average of these two, this plus this divided by 2, or any value in between these two, and normally the lower limit is chosen. So our tag or our encoded message will be 0.5408. So these calculations are for character D. So our message DAFDA is encoded with this tag. Now the question comes how to decode. We will take the same tag value and decode it. Say the tag value or encoded message is 0.5408. So how to start? Start with the same 0 to 1 interval. So this is say 1. And this is 0. While decoding also, you have to take care that you have to start from the below value or 0 value in the ascending order, right? So A is 0.4, D is equal to 0.4 and F is equal to 0.2. So here you can write the CDFs, or else even if you use the formula, you will get the same value. For example, say you want to find this upper level. So upper level is equal to lower level plus of difference into probability. So lower level over here is 0 plus of difference is 1 into probability is 0.4. So it is 1 into 0.4, which is equal to 0.4. Again, upper level is equal to lower level, that is 0.4 plus of difference, that is 1 into 0.4, the probability. So 0.4 plus 0.4, you will get 0.8. And finally, upper level is equal to lower level, that is 0.8 plus of difference is 1 into probability is 0.2. Okay. So 0.8 plus 0.2, it will be 1, right? Now start finding where this 0.5408 value exists. So it exists in between 0.4 and 0.8. So you have to expand these two values. Again, using the same formulas, you will find. So as our initial 0.5408 came for character D, the first character that is encoded is D. Now from this, find out where 0.5408 exists. It exists in between 0.4 and 0.56. So again we will expand this value, right? But this time we have expanded this portion which is for A, right? So our next character that is decoded will be A. So again finding these values. So now 0.5408 will exist in between, and finally we are getting 0.5408 as the lower limit, which we have chosen or which we normally choose as the tag. The last character will be from this lower limit to this upper limit. This 0.5408 falls in between this value and this value, which is for character A. So hence finally we have got our tag value as the lower limit, and we will stop the decoding process over here. So therefore, now let us implement the same characters in MATLAB and also cross verify whether we are getting the same values or not. So this is the program for arithmetic coding and decoding of a string. Print that string and display the length. Then we will make a lookup table in which initially we will keep value 0. Then using a for loop in z variable we find the occurrence of each character from string. And further in p variable we will get probability of these occurrences, and we will display both z as well as p. Next in CPR we will get the cumulative summation of probability from 1 till the last value of p, and in new CPR variable we are taking CPR from 0 to the last value of p. Next we will display CPR and new CPR, and we make a lookup table up to size of length of unique. So in the first column we are placing the new CPR values, and in the second column we are placing CPR values, and we display the lookup table. Next for encoder table, initially the lower limit is 0 and upper limit or higher limit is 1, and again using for loop from 1 up to the length and 1 up to the length of unique. If the string value from string matches with u, then that is the position of symbol in the unique string, and we increment it and we display. Next for getting the tag value of the matched character, we find out first the difference, which is higher limit minus lower limit or upper limit minus lower limit, and upper limit is equal to lower limit plus of difference into probability that we have stored in the table. Similarly, lower limit is equal to lower limit plus of difference into the first position of in the table, which is starting from 0. And finally we will find out the tag value. Okay, so the last lower limit will be our tag value, and we will display the tag value. Now for decoding, initially we take a blank string, and again using the for loops from 1 to length and length of unique. If the tag value falls between a certain range in the lookup table, then we will choose that particular probability from the table and modify our tag, and we get the matched tag character value in the decoded string. And we also keep on concatenating our string. Finally, we will display our decoded string. So let us run and see the output. The length of the string is 5. The unique characters are A, D and F. And the length of the unique character string is 3. Okay, why? Because D and A is repeating 2 times, right? Then Z is having value 2, 2, 1, A is occurring 2 times, D is occurring 2 times, and F is occurring 1 time. Therefore, it is 2, 2, 1. The probabilities are 0.4, 0.4 and 2. And the CPR values or cumulative probability values are 0.4, 0.8 and 1. And new CPR value will be ranging from 0 to 1. Then we make the table, and the lookup table is like this. The POS is 2. This means that the first character D is in the second position in the table. Higher limit is 0.8 and lower limit is 0.4 for the first character D of Dafda. Next, the position is 1 for second character A of Dafda, and we keep on updating the values of higher limit, lower limit and POS. So we are getting the same values as we got for our theory, and the tag value is 0.5408, the same value that we obtained for the theory portion. Next, we will decode our string and keep on concatenating characters one by one, and the final decoded string is the same. Similarly, we can use the same arithmetic coding for image lossless compression. But as I told you, the problem here will be that when the number of characters or number of pixels are very large, the floating point is very large, which cannot be handled by the computer. So same, we are using cameraman image and resizing it to 3 cross 3 only. In place of string, we are using numbers. So we'll be reshaping it to one dimension. So let us run and see the output. So you can see this is our original image and the decoded image is same. There is no difference in between the two images. That means it gives lossless data compression. So that is all for this video class. I hope you have gained a good knowledge from this video lecture. Thank you very much.